This topic discusses the critical factor needed to install process analyzers in the downstream refining industry. This topic in the Academy is contributed by Modcon, a UK-based company manufacturing and commissioning process analyzers in the refineries worldwide. This topic will discuss the challenges and trends faced by the refining industry to maintain product qualities due to continuous changes in crude oil quality. A refinery uses multiplexed process online or discrete analyzers to measure incoming crude oil qualities and outgoing products. The measured qualities may be different crude oil and end-user products. Many analyzer technologies are available in the marketplace based on required quality analysis, sampling points and response time, etc. Hence, there are many critical factors to select, configure, and commission a turnkey analyzer system. It is necessary to validate, certify, and maintain the analysis models and infrastructure. This topic discusses all the above considerations in detail. The global refining industry is at a crossroads, and the positive and negative issues associated with the business endeavors and operational commitment must be carefully examined. The industry has undergone a significant transformation in the last decade due to regulatory and market forces changes, such as fluctuating crude prices, tighter product quality, refinery emissions, shifting crude quality, and fundamental changes in fuel demands. The objective of a modern refinery is to manufacture high-value and on-specification products at optimal cost and minimal environmental burden. Therefore, online qualitative and quantitative measurements of physical properties and chemical composition are fundamental requirements. Process analyzers' success includes saving in production, product giveaway, operating workforce, and energy conservation. The modern refinery is a high-volume and low-margin enterprise, with feedstock costs around 90% of the cash flow. Therefore, refineries must reduce feedstock costs, decrease operating expenses, and increase product revenue to increase the margin. Optimization of petroleum products manufacturing, using advanced process analysis and control, enables us to reach the required quality at optimal cost and increase the conversion level and feedstock flexibility. In addition, recent developments in process analysis technologies significantly increase online utilization factors and reduce analyzer maintenance to ensure maximum efficiency of the refinery. At present, the refining industry must be flexible enough to respond immediately to feedstock changes and deviations in product demands due to the changing global economy. Therefore, blending operations become an effective strategy to answer the ever-growing competition between refineries. The strategy of blending crude oils and refinery products is to increase refining margins without affecting the required physical properties of the blends. Utilization of cheaper crude oils in crude oil blends and maximization of low-cost refinery intermediate products in final blends are basic operations to achieve this goal. Furthermore, online process analyzers are inevitable to operate the blending process efficiently and errorless. ASTM International, formerly known as the American Society for Testing and Materials, is an international standards organization that develops and publishes voluntary consensus technical standards for a wide range of materials, products, systems, and services. Some 12,575 ASTM voluntary consensus standards operate globally. Due to commercial, safety, environmental, quality, and processing reasons, there are many quality parameters and related test methods for petroleum products. The most common parameters are flash point, sulfur content, viscosity, acid number, API gravity, Reid vapor pressure, distillation, freeze point, Raman octane number, and chemical composition. For every one of these methods, many different types of laboratory instruments can perform offline measurements of samples from the process. Basic steps to process analysis include choosing the analytical method, sampling and sample preparation, proper location and housing, communication to control system, and reporting. Process analyzers' sample probes and sample transport lines are designed to ensure representative and rapid sampling, avoiding a possibility of contamination or dead volume. Typically, Complete integrated analyzer systems and all related services can be provided by experienced system integrators. Process analyzer systems are installed in the unique analyzer houses, including air conditioning, power distribution, lighting, termination and junction boxes, gas and flame detection, appropriate piping, and wiring. In addition, the process analyzer sample probes and sample transport lines are designed to ensure representative and rapid sampling, avoiding a possibility of contamination or dead volume. Sample conditioning systems to provide the sample in a state and condition compatible with the measurement technique used by process analyzers. Sample recovery systems, stream selection facilities, telephone modem connections, furniture, special equipment, tools, etc., are all an integral part of the process analyzer systems. The following critical factors shall be considered for analytical method selection and system design: accuracy and sensitivity, initial investment and maintenance costs, selectivity and cross-interference, single and multi-stream applications, sample handling and sample conditioning, reference method and calibration standards, and validation procedures. At the earliest system design stage, the process stream must be appropriately defined in operating conditions and complete sample composition. Then, the complete roadmap for process analyzers project implementation should be established by considering the following critical success factors: define measurement technique to be used, define process streams and components to be measured, proper sample system design and installation, complete solution, analyzer housing per IEC requirements, analyzers validation per ASTM and other standard regulations, and ongoing maintenance and support. Since the process analyzer results must be correlated finally against the standard laboratory methods of analysis, it is essential to select the analytical method from all available techniques correctly. We have also to distinguish between ASTM-based analyzers and correlative analysis technologies. If possible, always consider various spectrometry technologies, which are more reliable and easier to maintain than all others. ASTM-based discrete online analyzers are not depending on feedstock quality and other external factors, which gives a better correlation with the laboratory. However, their response time is usually longer and maintenance is expensive. These technologies are usually selected if no more reliable and proven technique can correlate well with the standard laboratory ASTM method. Process gas chromatography, or PGC, is a common type of discrete analyzer used in analytical chemistry to separate and analyze compounds that can be vaporized without decomposition. Despite its high maintenance requirements, this technology is the only available solution in many applications, where multiple components shall be measured with high accuracy. This method also requires the supply of high-quality carrier gases, hydrogen, nitrogen, helium, or argon with 99.995% or higher purities. Correlative online analysis methods are faster and less expensive and include spectrophotometry, NIR, FTIR, and magnetic resonance techniques, or MRA. However, validation of correlative analyzers against standard laboratory methods is only possible using special ASTM procedures. These factors should be seriously considered at a time of analyzers' performance validation and acceptance. Chemometrics is the chemical discipline that uses mathematical, statistical, and other methods to employ formal logic to design or select optimal measurement procedures and experiments, and provide maximum relevant chemical information by analyzing chemical data. The chemometrics approach uses multivariate methods, i.e., all variables are considered simultaneously. In this way, the model is fit to the data. When building a model to fit the data, the conclusion should be in harmony with the information present in the data. Chemometric data analysis and modeling necessitate appropriate quality, meaning accuracy and precision, concerning what data represent, irrespective of whether they've been acquired in the field, laboratory, or industrial, aka the process. The following trinity must be recognized and respected for chemometric data modeling to succeed. Data must be acquired by representative sampling, ensuring accuracy concerning the lot represented by the samples, and precision concerning all sampling process errors. Data must have an appropriate analytical quality, usually the least of the problems, as most analytical laboratories strive to be certified or accredited. Chemometric data models must respect a demand for reliable performance validation, for example, regarding prediction, classification, time forecasting. Data preprocessing is a substantial challenge in a chemometrics workflow. Sequentially, several steps are performed, and thus the number of combinations grows exponentially. Every individual step influences each other, complicating developing a general protocol that will always work. For example, one of the possible pitfalls is insufficient data pre-processing. Once this has happened, the subsequent analysis of the data will be influenced, and thus wrong conclusions may be obtained. Sample conditioning systems provide the sample in a state and condition compatible with the measurement technique used by analyzers. Process sample probes and sample transport lines are designed to ensure representative and rapid sampling, avoiding a possibility of contamination or dead volume. Without representative sampling, the entire chain of evidence versus the lot characteristics is flawed because of the ever-present heterogeneity of the material at all scales. The same holds if the precision of analysis is inferior. It is impossible to correct these deficiencies in the subsequent data analytical modeling. As analytical errors are typically 1 or 2 orders of magnitude smaller than the combined sampling errors, every aspect of data quality in practice hinges overwhelmingly on the sampling, either fully representative, acceptable, or non-representative, worthless. Analyzers and analyzer sampling systems require varying degrees of protection depending on the sample and the type of analyzer, the importance of the application, and the environment in which it must operate. Where the construction and maintenance requirements are not suitable for the working environment, additional protection, such as AHs, should be provided. This additional protection ensures the satisfactory performance of the instrument and facilitates maintenance. The first type of analyzer's housing is analyzer cabinet, which represents a small housing in which analyzers are installed individually or grouped. Maintenance is performed outside the cabinet with the door or doors open. Analyzer shelter is a structure with one or more sides open and free from obstruction to the natural passage of air, in which one or more analyzers are installed. The maintenance of the analyzers is typically performed in the protection of the shelter. The analyzer house, or AH, is an enclosed building or part of a building containing process analyzers and associated equipment. Process streams for analysis are brought in and regularly entered by authorized personnel. Analyzer systems are installed in the unique analyzer houses, including air conditioning, power distribution, lighting, termination, junction boxes, gas, flame detection, appropriate piping, and wiring. So-called smart analyzer houses is an effective solution for integrated solutions per the international standard IEC 61285-2004. This house typically includes sample conditioning systems with sample recovery and stream selection facilities, air conditioning, power distribution, lighting, termination and junction boxes, gas and flame detection, and appropriate piping and wiring. The trend over the past years is toward remote access to the analyzers and the house facilities across the internet for advanced monitoring and technical support. This facility enables remote and predictive maintenance of analyzers and sample conditioning systems by directly deploying a unique security appliance in front of the analyzer house communication network. Typically, analyzer houses are delivered prepared and pre-wired with all analyzers, sample systems, and utilities installed at the factory. The complete assembly is tested and shipped to the site as a single package. In this way, site installation work is kept to a minimum, thanks to turnkey responsibility when one team of specialists manages the project from start to finish. These systems are typically equipped with the following main facilities: air conditioning, power distribution, lighting, termination and junction boxes, gas and flame detection, relevant piping, and wiring. Process sample probes and sample transport lines are designed to ensure representative and rapid sampling, avoiding a possibility of contamination or dead volume. Sample conditioning systems provide the sample in a state and condition compatible with the measurement technique used by analyzers. Sample recovery systems, stream selection facilities, telephone modem connections, furniture, special equipment, tools, etc. When a new stream analyzer is initially installed, or after significant maintenance has been performed, a set of tests must be performed to demonstrate that the analyzer meets the manufacturer's specifications, the historical performance standards, and the specification limits set by the process being analyzed. These diagnostic tests may require that the analyzer be adjusted to provide predetermined output levels for certain certified reference materials, or CRMs, or compared with other reliable analyzers. The methods of validation calibration rely on effective coordination between analyzer maintenance forces and the laboratory. Therefore, there must be efficient and effective communication and mutual agreement between the process analyzers department and the plant laboratory. ASTM develops standard procedures to validate the process analyzers so that all problems could be solved quote-unquote under one roof, and an agreed position taken to benefit process operations. Standard practice for validation of process stream analyzer systems ASTM D3764 describes procedures and recommendations for validating a total process analyzer system, or its subsystems, or both, used to directly measure the physical or chemical characteristics of petroleum and petrochemical products. Validation is achieved by statistical assessment of results generated for common materials by the total analyzer system or its subsystem versus results generated by an ASTM or other established primary test method, or PTM. For analyzers used in product certification, the analyzer system precision determined by the statistical assessment is typically compared to the site precision for the PTM. For other analyzer applications, analyzer system precision determined by the statistical assessment is compared to pre-specified performance criteria based on the intended use. Typically, the following on-site services shall be provided by system integrators after analyzer systems installation: equipment assembly and erection supervision, pre-commissioning and commissioning, connection, wiring, and system integration, startup, setup, software configuration, and alarm handling configuration, calibration, validation, and SAT of the complete analyzer system, training of customers' operators and maintenance personnel, fulfillment of any warranty obligations and performing any repairs required, and long-term analyzers maintenance and remote technical support and consulting. The ultimate effectiveness of the contribution of online analyzers is measured by the ability to perform their functional requirements upon demand. Once the functional requirements are identified, the following clauses shall be established to give guidance in achieving the solutions, with the aim of maximizing performance and benefit of installed analyzers, achieving complete operator confidence in the use of online analyzers, ensuring that the analyzer output data is becoming reliable enough to be used by operators, control systems, and other users to improve plant operation, and measuring KPI for the performance and ROI of the analyzer system. This well-established methodology optimizes analyzer performance targets by balancing maintenance costs and benefiting the process. In this topic, we have considered the process analyzer technologies and the critical factors for the successful commissioning of the analyzer system. It cannot be stressed enough that a lack of post-commission maintenance can waste all efforts and resources to use the analyzer system effectively for years to come. OMS eLearning Academy thanks ModCon for contributing this critical content about the process analyzers. We hope you have gained practical knowledge in this topic to help you understand process analyzers in the downstream refining industry.